All right. Good afternoon. It is my pleasure to introduce Jérôme. So Jérôme doesn't need a lot of introduction because he's well known and well liked about us. So, huh?
It's a lazy car wash.
So Jérôme has been with us for a few years, and he's very much interested on machine learning methods that had to do with PDEs, measuring data, analyzing data. It's quite broad, and we asked Jérôme to give a kind of a general talk about some of the stuff he has been doing, working with us. So that's why I don't need a big introduction, because actually the talk is going to be about some of the stuff he has been doing with us for a while. And thanks for coming, and the floor is yours, Jérôme.
Thanks for the improvisation.
Introduction.
Okay, so yeah, as Ricardo said, I've been asked to give you a very general talk about what I'm doing. There will be a short section of math and then applications. Okay, feel free to interrupt me at any time. Any question, shoot. First, what is data science? Your definition.
Science that includes data.
Okay, that's the easy answer. Well, actually, I checked the definition online. If there is a definition, I found on Wikipedia.
Oh, wow.
That data science is an interdisciplinary field that uses scientific method processes, algorithms, systems, blah, 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 to extract knowledge. So it's very general, right? I mean, we heard the word data science since what, a few years now? But honestly, I think people do data science since back to the 40s, 50s, maybe. It's just that now we have those fancy words, right? We need hashtag something right today, right? So one thing is data science is related to data mining, machine learning, and big data. I kind of disagree a little bit about that, because I think there's other methods that do data science which are not related to those. Even though it depends what exactly we mean by data mining. That's another debate. Okay, so what I'm going to show you today, because my main application is about signal and image processing, and I'm doing some applying math methods to do this kind of thing. But I'm going to focus on two main things from the mathematical point of view, which are signal or image restoration or decomposition, right? And I will explain what those work means. And then another topic, which is kind of my empirical WebEx, and I will also show you what goes on. In terms of application, I'll show you how we can use those tools in those applications. Atmospheric turbulence mitigation, texture analysis, that's image processing. And this one is kind of an application of this one, which is in collaboration with chemists from UCLA. They have this very intense microscope, scanning, tunneling microscopy, and how we can actually use this kind of techniques to extract chemical and physical information from those images. Okay, let's talk math first. First, about signal and image restoration. So what's the issue here? You have a physical quantity, just an image, or you take an X-ray to be inside of the body, whatever you are imaging, right? So that I will denote that quantity, right? But when you acquire that quantity, so you have some acquisition process, and that acquisition process do involve several things. In particular, equipment is involved in the acquisition, right? When you have a camera, there is a lens, right? And that lens does impact what you are actually measuring, right? The environment also can play a role. That's what I will show you with the atmospheric turbulence. where you see that the atmosphere itself does impact what you are measuring on your sensor, right? So you can have several things that can impact what you are measuring on the original node, right? And so what we get is an observation that we do not have. Eventually, on top of that, you could have also some noise. That happens almost all the time, right? So what we get is something that will be my observation, will be some operator. That's an operator, right? A, whatever it is for now, just something that corresponds to that box, right? So that thing does something to your original signal, and then you have noise. So here I'm considering an additive noise, but there exists some system where the noise is multiplicative. It could be an AU times N, right? Like, for example, in radar, that's a multiplicative noise. But I'm going to focus just on
So
yes.
you're not assuming that the operator A is linear.
It depends. For some problem, it can be linear, for some, it cannot. So I'm assuming nothing like this.
Jérôme, typically the noises come from environmental variations or equipment.
Not only, it could be the sensor itself. For example, in infrared images, if your sensor is not cooled down enough, the sensor itself generates some noise.
But isn't that on the part of the equipment? The sensor is the equipment, why is that outside?
That thing more or less built into that. Yes, I agree. It could be a bit more complicated.
Assuming it's independent and correlated.
That's the point. Most of the time, we consider the noise is independent from what you are looking for, unless it's multiplicative. In that case, you may have some correlation. But I'm gonna just assume it's additive. That is independent of that. Yes, that's a good one. So now regarding that operator A, if A is just the identity, so basically there's no A, F equals AU plus N. When you want to retry U from F, that's what we call a denoising problem, right? You just want to remove the noise. If now A is a convolutional kernel, so that's what we call a deconvolution problem. And for example, when you have a blur in an image, that a blur can be modeled by this kind of thing, by convolution, right? And you want to deconvolve those. The issue, most of the time here, is that that operator is not invertible. That happens most of the time. I would say 99% of the time, maybe, right? So that's why you need specific method in order to do the restoration. Another example is when A is a sampling matrix. For example, the most simple example, you take one pixel and you take the information every other pixel. So you are missing some pixels, right? And you want to reconstruct an image. So that's what corresponds to some interpolation or eventually super resolution problem. Yeah. So depending on the type of operator you have, you may have different type of problems. You can also eventually combine them. Because actually, when you do super resolution, most of the time you have a combination of both. Okay, so that's the main framework. Okay, now how can we address this type of problem? So I'm not talking about machine learning right now, just math. Okay? The way we usually go, so first there's two main cases when the operator A is known and when it's unknown. So that's what we call the non-blind and blind case. Right? So in that case, what we want to write something that depends on the input F, the operator, right? And we have some term that we call a regularization term about what we want, about kind of the assumption you are doing on the image you are trying to reconstruct, right? And you want to minimize that thing with respect to U. And if it's a blind case, you minimize respect to A as well. But in that case, most of the time, you need an extra term that does regularize your kernel A. Right? So it's basically a minimization problem. So now, of course, the main question is how do we choose those different terms? Right? And that's where your knowledge of math comes in. Right? And in practice, what we do is so an image is basically an image, or a signal is basically something that is a function, and it does belong to a certain space of function. And those spaces of function are most of the time we use norm spaces, so they do have specific norms. And so it's by choosing appropriately those spaces, and then we use those norms as our regularization term. So for example, here, that's a denoising problem. That's called the Reading, Osher, and Fadeni model, which is one of the most cited primary papers. Almost 1 million citations. Where you have your image F minus U. Yes, what I didn't mention is that term D here. That's what we call the data fidelity term. That's a term, its purpose is to make sure that the reconstructed image U still remain close to the observation F. Right? You don't want to reconstruct something that does look completely different than the observation. Right? So there might be some similarities between the reconstructed one and the observed one. So here, this is the term D. Right? And since it's a denoising, there's no A. A is the identity. So here I'm just taking the energy of F minus U. By the way, the square is so that measure basically, I mean, when you minimize this quantity, you see that the minimum would be when it's equal to 0, when U will be equal to F. Of course, you don't want U equal to F because it means you do nothing. Right? So that's the goal of this term. So this one, what does it do? It's basically assuming that the function U belongs to the space that we call D, the space of bounded variations, which basically corresponds to measure the L1 energy of the gradient of the image. Okay, so what happens is we have markers. Does someone have a marker?
Yeah.
Should we have TS here? So what happens is, for example, if you have, let's say, a function like that, right? What you actually measure is the same thing between nodes. Right? And you want to reconstruct a nice step function. The point is the step function itself, if you take its gradient, 0, then you have a jump, 0, right? And so the L1 norm comes out that the L1 norm does follow sparsity. Right? And sparsity means it promotes the fact that you have only a few values that are different from 0. Right? And so if you want to find this kind of shape, you want to have the gradient to be sparse. Right? Because if you take the gradient of the noisy one, then you will have a lot of information everywhere. But if you use the L1 norm to penalize gradient from the noise, right, you will promote to have this kind of gradient, which corresponds to a function that you set base. So that's very well known.
So I understand what you're doing there, but aren't you also gonna smooth out your the image that you're trying to actually recover because you are minimizing that gradient?
No. No, that's one nice property of the space. It keeps sharp edges. If you were using an L2 norm, in that case, yes, you're gonna smooth the edges. So if you use an L2 norm, that's called the Tikhonov algorithm, and this one smooths out the edges. And that's basically why this algorithm became so popular, because when they just realized by changing the norm here, boom, you have very nice sharp edges. Bingo, right? Plenty of citations.
Well, what's the rationale for mixing L1 and L2?
Well, so L2 is just saying we measure the energy of the difference. So it just measures how different U is from F. you're right, we could use other norms as well. I mean, there are papers that are using also L1 and other types of norms. Yeah.
So the idea that the noise has distribution, like it could be a Gauss.
Yeah, exactly. You should basically the L2 norm corresponds to the fact that you are assuming that the norm is a Gaussian distribution. But you could use other norms.
Related to that question, because they're mixing norms, obviously there is no recipe to find lambda. Right? So it's basically the way between the two.
Yeah, so
is there a way to actually know a priori what to do with lambda?
So lambda is an hyperparameter, so it become more or less denoising we want. There are some attempts of also optimizing lambda. There is some interesting method that actually give pretty good results. The worst thing is they are very computationally expensive. And so in practice, nobody uses them.
So you move the lambda and it's you,
yeah.
You use it that judges. So in the end, you're going to use a human optimizer in the end for lambda.
What we can see starting right now, people are also trying to do some kind of machine learning techniques to learn what should be lambda. So we see this kind of thing showing up in these last years. Yeah. But at first, when those algorithms were proposed, yeah, it's the operator is doing it. Which, depending on the type of images you have, sometimes you can choose a lambda very small or very large, depending on how you choose. Yeah? And it works for all your images, that's fine. So that's for several cases, the sensitivity to the choice of lambda is not too bad. So you can choose one, keep that, and it's always that going.
Because even within humans, one human will say that one lambda is the best, and another human will say, no, that's not the best. This lambda is best. They're just looking at different things, and they're going to realize, I like better this one, and you like better that one.
When I say human, it's not necessarily I, but the fact that you can compute the, for example, the PSNR, signal to noise ratio, right? Quantity that measure basically how good is your restoration. And so based on that, you have actually a value that tells you it's better by choosing this.
Since lambda is a free parameter, is there any reason for making it lambda over 2?
Well, because I forgot that square.
Oh.
And when you take when you differentiate, it's just to cancel the 2. That's it. But yeah, I forgot the square. That's something to play with. So that's a denoising case. When A is a kernel, convolutional kernel, and you don't know it, this is, for example, the Chan blind deblurring algorithm. So you see that they use the same regularization for the image. They use a similar regularization for the kernel, which depends on the type of kernel you are looking for, right? So that could be discussed. And same type of data fidelity term, but you have your kernel for A that shows up. And now you minimize respect to both U and A.
So what happens to the differentiability when you go to a one node?
Well, you can actually do, there are some assumptions that you can use to make things that never go to 0. And so you are in a part where it's differentiable. That being said, the algorithm that we use today don't use differential. We have way more efficient algorithm than the one that we are trying to using some calculation of variation, right? That we are the first algorithm that we have proposed, but today we don't use those things anymore because you have way faster algorithm. Typically today it's the primal dual kind of algorithm. Those are way faster and way easier to implement.
So the L1 norm apply to the grading, you give the edge preserving characteristic. Is there any similar interpretation for the term in the
Yeah, because okay, in the original paper of Chan, they were mostly focusing on motion blur. And it turns out that the kernel of such blur is kind of piecewise constant. So that's why they consider that case, that it was kind of, I mean, the kernel looks like something like that. right? So that's why they consider it. That's why I said,
Stay to the foreground.
yeah. So that's why I said we can discuss that choice. For this type of blur, yeah, it's nice. For other type of blur, that's okay. Now there is other choices because the miner you can choose projecting your image view into another domain, like wavelets, Fourier, I mean, many different kind of things. And then you minimize. So the point is, the wavelet representation of a natural image is a sparse representation. And so that's why you can promote the sparsity. That is and those works very nice as well. So you can do a lot of things. And those correspond, for example, to choose a different space. That's what we call a base of space. That's that's all. That's pretty stuff. But that space is actually very close to that one, depending on certain conditions. But that's also pretty easy to if you are curious to see this type of implementation, I think this one. I do have some MATLAB code on my webpage called the Bregman codebook. So it was not using the primary dual techniques that we use today, but the one before that's called the Bregman iterations. There's 3 codes if you want to see what those things looks like in practice. So these are on my webpage. Any other questions about this? So it's just to give you an idea how we proceed, how we build a model to perform some restoration. And I'm going to show you how we use this kind of thing later in the application. Yeah, that's what I just said. Okay, the other thing is what I call the empirical wavelet. So I'm guessing most people have no idea what a wavelet is, just a standard wavelet. Basically, it's simple. You have what we call a mother wavelet, which is just something that oscillates like that, mostly compacted, right? And you build a family of wavelets just by doing dilation contractions and translation. Okay, that's how we build a family of wavelets.
You're not changing the decay rates. The decay rates are always the same.
Yes. So there is a two norm of CAB, the same as the image. You could do another way, because that way. So it's just this is A just doing the dilation pattern, depending if yes or larger than 1, and B just translates. Right? And what happens is you have a signal, basically a kind of compute, so it's a linear product. Again, it's a linear product where you are doing just the projection of your signal on all those positions of those wavelets with different dilation. Right? And that gives you the wavelet representation.
So you have a complete basis? Orthogonal complete basis?
You could build a normal basis of L2, yes.
But it's important for those bases. I mean, even if it's not complete because of the application, it's the decay on the coefficients.
So there are some theorems that shows that you have some sort of decay.
So you can truncate somewhere.
The same type of property as for the Fourier transform. Yeah, you have this kind of property.
Just a related question. I mean, can you select your side to have finite support?
So well, there's a whole theory, right? That could be a compact support. That could not be a compact support, but relative. You cannot choose it to be very spread. Does not make sense. There's also several ways. I mean, 2 main ways to do such waves: the time domain or the Fourier domain. Right? So that's 2 different ways. Right? I mean, yeah, there exists so many different other wavelets. But I don't know all of them. That's too many. Each one has its own particularities. for example, the Doveshis wavelets, they correspond to have those wavelets to have a minimum, well, the moments of those wavelets are 0 up to a certain. That's very important. For example, they developed those things because they were looking at finding petrol in the ground. So when those things, then the signal comes back, they measure this, and they needed to have certain moments of those wavelets to be equal to 0 in order to be sure that they eliminate some characteristics from the ground. Right? So that's why they develop those things. So depending on the type of application you have, you may choose one type of wavelet or in neuroscience, the most used one is the Morley wavelet. There are some good reasons to do that, but in my opinion, that's not the only choice.
I observed the same thing. I was just wondering if you have some sort of underlying neurodynamic model of what's going on, you can show us how to come up with the best wavelength instead of
Kind of.
kind of.
Yes, yeah, more or less, yes, right. So another way of seeing what those wavelets to extract some. At the end of the day, you can extract what we call the time frequency pair. Let's say time frequency, right? Meaning that it tells you at a given time how much of a certain frequency you have, right? That's a very useful information. And so wavelets allow us to do that because there is basically a inverse link between the scaling factor and frequency. There's a coefficient involved that depends on the model wavelet. But here the point of view is we want to extract some specific information that corresponds to certain frequency. Okay, so keep that in mind. So here, that's why I want to extract harmonic modes. So those harmonic modes are what? Just amplitude modulated, frequency modulated signals, right? And we are assuming that those things are not going crazy. So they stay within a certain range, right? But you have, each FK is one harmonic mode, and your original signal f of t is just a sum of such modes, plus eventually a residual, right? You don't write it here, but you can do that. So in practice, how can we do that? That's, for example, that's a toy example. So that's a spectrum, the Fourier spectrum, in blue, right? And it turns out that such thing here does correspond to something which is quite compactly supported in the Fourier domain. So basically, 1 in 10 here corresponds to 1 FK, right? So that's our assumption, that things are not completely mixed up together, otherwise it's a different problem, right? But here, if they are sufficiently separated, then consider those are different harmonic modes, right? And so the goal is just to detect separations between those different mountains, right? Because something I didn't say is the Fourier domain, in this kind of family, the frequency line, depending how the method you choose to set up A, the scaling factor, and most of the time we just put A equal to the N. So that corresponds to basically divide by 2 every time, right? And on each super corresponds the Fourier transform of the corresponding N, right? The point is, such method is prescribed without taking into account the signal inside, right? So the main issue is, looks like it's not me. So the main issue is that if, for example, your mountain goes here, that means you have one wavelet that will capture one part of that mountain, and the other one will capture the part. So you are splitting information. You are breaking information. Right? So the idea of this method is when you detect the position between the different modes, now you know that one wavelength will capture one. Okay, that's the idea. Yeah, here we go. Right, so that's what we are doing. Here we have, then now we have a wavelet method that's adaptive to the input signal. Okay. How we build the wavelet filters? Well, that's in the Fourier domain. This type of shape. Basically, zero outside. So the omega and are those red boundaries, right? We define a transition area here just to have a certain degree of smoothness here. Nice. Even though now I actually can't use any kind of other wavelength. You have those transition areas, one here, zero outside, and that choice became from some tools in math that's called the Littlewood Palais operators. And so this is an example of what you get. That's an ECG signal per bit, right? And in particular, on this one, you see that you have this kind of time thing, and that's actually the 60 Hertz from the network. I don't know why it showed on the recording, but it was there, right? So you have the ECG signal on top of that sign. The spectrum is this one. Here I forced to have only 5 modes, right? Just too much to put. And those are the different harmonic modes that you get. In particular, you get back this one very nicely. And the 60 Hertz is actually a kind of a combination of mostly. So you can extract the harmonic modes from any signal. And today we have a method where we actually don't need to choose the number of modes. It's fully automatic. Just give the signal, the method finds for you the number of modes, and it builds automatically the filter to the transfer. So today it's 0 parameter, except the choice of each type of filter you want to use.
You need to have a cut on the amount of energy that you are measuring. So that's where you are going to eventually decide that from that point onward, you're not going to have more modes. How can that be?
I mean, in practice, in the digital world, we have a finite number of samples. So I consider I'm between 0 and 5, just normalizing things. Right? And so I'm working on this interval and just splitting that interval. So now, of course, if you consider the continuous case where your spectrum can go to infinity, I do have a paper, a theoretical paper, where I give some framework on how we can write things properly in order to make sure, I mean, that basically you can decompose the whole waveline using different type of partition. You can have an infinite partitions, or you could have what I call the infinite rays, where at some point there's no longer any detection, and you have one big thing that covers the entire remaining, either on each side. So, and we can write things this way. So I develop all the formalism to do this kind of things. We have that.
You work with EEG.
Yeah.
And typically what researchers do, let's say you have 5 minutes, they wouldn't do a power spectrum of the whole thing. They would take some window size, say 10 seconds. And you maybe do overlapping windows and you get this average power spectral density. Then there's something else that reminds me of, I don't know how it would relate, but something called singular spectrum. Singular spectrum analysis, where basically you march along you just shift by one time sample throughout the whole continuous recording, and then you do PCA on that. I'm sure
that's something completely different. I mean,
yeah.
Those methods are not trying to focus on extracting harmonic modes, but they are trying to find some sort of eigenmodes, right? So it's slightly different.
So how would you, like, in principle, let's say you had 5 minutes of EEG or ECG, with like a long recording. Would you break it up into chunks like that, or would you keep?
Right now, no, I will do the whole thing. Now, there might be an advantage of breaking things down, is that if your each EEG signal is evolving enough in time, then the position of those bounds and eventually the number of modes might have changed. So you eventually in time you can also adapt the filters evolving themselves. Right.
Nice.
And in that case, what you could do is plot the time frequency plane, and you may have some sort of a video, right? A time frequency plane that depends on time. So that should be doable. We have never done it, but it should be doable. Okay, quickly, extension in 2D for image processing. So the main point was just partitioning the Fourier domain, right? That's the key point. And as soon as you have that partition, you can build your filters. So to generalize to 2D, and actually I'm working on the end right now. Same thing, you just want to partition your Fourier domain. And we have several types of partitioning. Those first three here, where they do correspond to some existing type of Weber transform, you just generalize them to be adaptive. The tensor case, you detect rectangles, right? And here the position of those rectangles is adaptive, right? Second case, that's the little palette type of operator, it's the radius that's adaptive, right? So each ring corresponds to one Weber. Those type of things is nice to extract different scales in an image, right? Without any specific direction, just the scale. The curvelet ones, so the original curvelet transform looks like this. Those frequencies, then you have one ring, double the size of the rings each time, right? And then you split, you have this, and so on, right? And every two rings you divide by two again. Right? That's the original curvelet transform as it was defined by Cordes and Dono in Stanford. But in our case, we said, okay, well, what we can do, we actually have three options. The first one, I detect independently the radius of each ring and the angular position. Option two, I detect the rings first, and within each ring, I detect the angular position. Option three, I start with the angular position, and within each angular sector, I detect the rings. Right? That's my three different options here. So those were still kind of using some prescribed type of partitioning. So then we can question, can we do something completely arbitrary? And the answer is yes, we can. Let's start with this one. Watershed. So here, basically, what you need to think is that for each one, you have a mountain here. So what we do, we detect the peak of those mountains, and from there, we find the lines of lower level, the valleys between the mountains. And there is an algorithm called the watershed algorithm that does that very nice for them to uncheck for watershed. So we have that here. And in order to still keep certain minimum of regularity regarding the geometry, eventually what you could do is basically simply you detect the peaks of the mountains, but you use a Voronoi partition. That was just accepted yesterday. So that's good. And so now we can do empirical web that we use different type of partition. Question on that? No? So, oh, that's just an example of the curvelet one. So that's a toy example. I use that image. So you have different harmonic modes here. The rectangle and the oval here are just the residual. And that's the so that's the detected, so that's option 2, curvelet option 2, right? And you have you see that the one area focuses one specific piece, right? So on. And those are the different components. So in particular, this one, and the last one is here. The other one, you can see them, but actually the energy was just normalized. You can see them. Otherwise, but those different, this one, they do correspond to the 4 different harmonic modes. Okay, applications. Let's talk on that now. So atmospheric turbulence mitigation. What's the problem? I have a sensor. I want to look at some target which is several kilometers away, right? Of course, in between we have the atmospheric turbulence. And you've all been to the desert, right? It's close from here. When you look very far away, you see things like moving, blurry, and so on, right? The goal is, can I reconstruct a nice clean picture from a sequence of frames, a sequence of acquisition? So I'm not considering I only have one observation, but I do have several. Those will be my FI. I corresponds to time, basically. And so the atmospheric turbulence, well, it's a very complicated thing, of course, but we take the point of view that it's a combination of geometric distortion and blur. Right? So you can see that as the PI will be the geometric distortion and H will be the blur. Now we are assuming that I mean, when you do the acquisition of your frame, it's within a few seconds, right? So the blur does not change much, but the geometric distortion changes. That's why I'm assuming H does not kind of time. Right, but only the geometric distortion. So removing the geometric distortion, that's what we call a stabilization algorithm, right? And the way you can do it is basically minimizing this type of thing. J is nothing else than my thing before, L1 norm of the gradient. So that's in here, and we have this data fidelity term, but now we take the sum of all with respect to all frames, right? And we minimize with both the stabilized image and the geometric distortion, because we don't know this geometric distortion, so we have to estimate those. We can do that pretty efficiently by using the optical flow algorithm that measure the displacement between two images. So we use that. Not gonna go to the detail, but it was very nice. And then you have the deblurring, and the last algorithm that we have to develop is based using a very specific kernel that's called the Fried kernel. David Fried in the 1960s wrote a series of papers on the impact of the atmospheric turbulence in an image. And it turns out that crazy physics, mix of physics, turbulence, with several things, crazy paper. But at the end, the interesting part is he gave an explicit expression of what is the kernel that corresponds to the blur due to the atmospheric turbulence. And so we use that thing. At first, the first time I used that, I tried to directly use the expression of that kernel, but it's quite complicated because there are some parameters that are not easy to find unless you have measurements, right? But you do not have any practice. So what we did with the 1.5 is we just re-expressed that kernel in a different way, the more mathematical way than physical way. And so basically we wrote the kernel in a general form like this, where in the case of the Fried kernel, we only have n equals 2. And those different coefficients correspond to those things. And the function, so f1 corresponds to that function, f2 corresponds to the f2. And so the goal is, instead of having those equal parameters, these few, and those, v is a completely nonlinear function, so it's very hard to estimate those parameters. Instead, we take the point of view, let's just estimate the AI direction. Don't go to the physics, but just estimate the coefficient there. And so we set up this function over here. So that measures the data term. We have a regularization on the coefficient, so on the kernel itself. That's just to make the algorithm to behave nicely. And actually, we can directly estimate the lambda. So that's a nice thing. And R of X, that's just my regularization on the reconstructed image. Right? And we use a very particular thing, a bit more complicated than the norm that I showed you before. So non-local patch kind of things. But it works very nice. And I need to show a video. Well. So that's On the left, that's my FI, my sequence of frames, right? Here is the stabilization. Use the deblurring, yes. Right. So you see that if you look at all those small bars, you see that they are mixed in sometimes, right? Now we have a nice separation between those bars, and the edges are very sharp. So that's what we get here. You have other results. Those are that's some images we actually of the football field. That's the blurry case. It's hard to see on the project. But you get way sharper. The texture are way more defined. Actually, there is a fence here that you can see, and you can see it on this image. Those two are sequences acquired in New Mexico quite a few years ago. Those things were at 2 kilometers, like that, so like that, 2 kilometers away. And so it's better after the restoration to read the and that's a sequence from the Navy, where you also have a lot of details that you can see those pores, several things, the background. So that algorithm works pretty well. Okay. Any epileptic people in the room? If you are epileptic, don't watch the screen. The next problem was to detect a moving target within the atmospheric turbulence. What you see here is the movement flow. So a color corresponds to a specific direction. Right? Red means moving this way, blue means that way, and so on. Right? There is a moving target there. Can you see it?
And even I know what it is, where it is, because I've seen you talk before. Not even knowing where it is, I cannot see it.
So what we did here, we use some decomposition method. Let me show you. So we decompose those flows because if you look at basically a frame time, right? And if you take that 3D point of view, that space-time point of view, what happens is the moving target follows one particular pattern, right? Assuming there's no joint people, right? Close, right? So it follows a certain pattern. And now what happens is you can see that whole thing as a combination of something that looks like a piecewise constant term plus some oscillating patterns, right? And it turns out that we have very nice decomposition algorithms that do separate piecewise kind of function and oscillatory functions. And that's this type of thing here that we can do. So I'm not going to go to the details again, but it's just minimizing. So U will be the piecewise component, and the other one will be the oscillatory part. Right? And we minimize again that including the appropriate norm. C here is the curve transform, not the empirical one, the standard one, but it works nicely as well. So we can minimize this thing, and what we get is this. So U, B, right? Oscillatory part, the constant part, and now the target is there. You can actually extract the target from that crazy flow. So it works nicely. How much time do I have? It's almost time.
10 minutes.
You guys have so many questions.
We haven't seen any questions. So we might not have that many questions at the end.
Okay.
So students, you can start asking questions because there's not going to be a lot of questions. And
Okay, I can go fast on the last part. Texture segmentation, right? You want to extract different type of texture in an image. There are several ways of doing that. So what happens is in practice, you want to extract some specific features because we know that you cannot characterize the texture just from the pixel information. That does not work. So you need to extract specific texture features. There are several ways of doing that to occurrence matrices, binary patterns. Wavelets are very good, and there is many of them. When you have those features, you feed that to a classifier or a clustering algorithm, and you can do some texture segmentation, right? Of course, what we did is using empirical wavelet, because textures do have very nice harmonic properties. And so I said, that might be the best way to go. And we were totally right. So first case, there's no learning here. We just extracted the features. So the empirical wavelet coefficient, compute the energy of those coefficients, feed that to just a K-means algorithm, about one of the most stupid clustering algorithms. Here are different type of wavelets. So each time it's EWT, that's the empirical one, right? And you see that every single time. Those are different data sets. And we are always dealing with classic methods. Standard curvelet, Gabor are the most used wavelets for texture analysis. They are way better than those. And those are different type of wavelets. That's the unsupervised case. Of course, next we try, example in practice. That's a toy example from one of the data sets. We have 5 different textures, right? This is what you get. This is what we get. That's the ground. And you can see that the other ones are worse than ours. It's not perfect, but they are worse than ours. Next, of course, we said, well, okay, there are neural networks that do texture analysis, texture classification. We perform it nicely, like around 70, 80% of the classification. What happens if instead of feeding images, we first do the empirical wavelet decomposition and we feed the empirical wavelet coefficient? We just did that, just as a pre-processing. We try on several types of networks. So that's an example in the FCMT. We just added the WC here, right? And we feed that to the network, we retrain the network, evaluate on the same data set. And here is what we get. EWT, so non-EWT, EWT, okay, for the same network. Something here, something here, and those are different networks. The results are way better, way better. To be honest, when my student came in my office and showed me the results, I said, no, you're wrong, it's not possible. He showed me the results. We are going from between 70 and 80% to between 95, 99% for good classification. At first, I didn't believe it. I said, no, come back next week, retry. Because that's not possible, it's too good. And actually, he came back with the exact same results. And we published those results, and there is the Prague data set. They do have a website where they capitalize the results of all algorithms, and everyone who has an algorithm can just download the data set. They have their own set of metrics. You want those metrics, you send them the results, they capitalize in the table. We ran first since almost 5, 6 years now. The first 2 lines in the table, it says nobody beat us so far. Someone is getting closer, but not yet above, right? So, I mean, that's pretty cool. So the empirical wavelets are doing pretty amazing work at capturing this type of information. As soon as you deal with some oscillating patterns and in harmonic modes, I believe that's the way to go. There's no question. You need to use an empirical type of thing. That's another result from another data set. And last application, which is basically kind of an application of that, the scanning tunneling microscopy. So you have a tip that's 1 nanometer width, right? So they scan the sample. You have a current that goes through the material and the tip, and the difference in the current corresponds to the molecular structure of the material. You can measure this kind of. And what you get is this type of image. So you can see this very nicely, but you have this shape and you have the image is actually changing by itself. That's interesting. And you have some texture on it that corresponds to the molecular orientation in the material. And so those folks from UCLA, they were basically using those images to extract some physical and chemical information, because they work on some theoretical model of the chemical processes, blah, 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 blah. Don't ask me the details. The point is, before we talk to us, they were doing the segmentation of those images, the different textures, using the mouse and the screen. So you can imagine how much time it takes to segment a bunch of images. So we
Digitizing?
what?
Like digitizing?
No, I mean they have the image on the screen and they have the mouse. They draw edges of the different regions correspond to.
Call an undergrad. You put an undergrad on the
Exactly.
computer.
That's basically what they
It's
were
not
doing.
in time. It's the
Yeah,
amount of undergrads that you put into the job.
They had an army of undergrads and spending their day drawing on the screen, right? So it took forever. Right? We said, come on, we have a segmentation algorithm, right? So what we did is we just did an image decomposition, so extracting those piecewise constant part and the oscillatory parts of the texture. So it's called cartoon and texture, the decomposition. And then we use specific segmentation algorithm for each component, which are very specific for the type of information we are looking at. For this one, so for the cartoon part, we use a combination of the Chang-Bézé model with a Ginsburg-Landau approximation. We give you a bunch of pieces, the NBO scheme tree. So that texture, we basically use the except that the student use just the key. That's it. And eventually, if you want, you can find the information from those segmentations. Not mandatory, but if you want, you can do that as well. And so, an example here. So that's the same image I showed you before. The spectrum of that image is here. They use a curved red type 3 here, right? And so after that, you get this type of segmentation. And so what happens is you get the different colors correspond to different chemical bonding directions. So that gives us the information about that. Another example is this one, and maybe that's the last one. That's the input image, right? Those are the different classes you can detect, and you get that final segmentation. And the nice thing is that, so regions 1 and 2, they correspond to what they call well-ordered regions. Region 3, which is kind of the interface with those regions, is the disordered region. If you look at the texture, you get the different molecular orientations. And you can, the point is you can correlate that with that information together. And that gives them a lot of information from the chemistry that is going on in the material. So those guys were pretty happy about those results. And way more efficient now. They don't have to need an army of undergrad students. And that's pretty much it. So if you want, first, my website. All my papers are there. If you are curious, you can check it out there. In terms of current and future work, now working actively on the theory behind the empirical wavelets. One of my master students is already put several theorems about how we get frames for the one decade. I'm myself working on the higher dimensions. We are also working on using neural nets to do the atmospheric turbulence mitigation. We already showed that if you use some existing deblurring algorithm, use the same stabilization I showed you, but using a neural net-based deblurring, you actually improve things. It works better than classic algorithm. And the student is currently working on implementing. There's just a few papers that try to address this problem using neural nets. So he's trying to implement those papers to see exactly what we get. So that's something we are looking at. And something I discussed recently with my colleague from UCLA is combining those empirical wavelets with the neural nets for the ST image. There's one question, which is we need enough data to train the models.
All right, thank you, Jérôme. I will leave a couple of minutes for questions, but only for students. I have not heard any questions from students, and this is like mostly students. So, students, any questions for Jérôme? Go ahead.
Yes. Well. Yes. And no. Yes, in the sense that you get an given image, you get one set of models. Now, in the case of yeah. This one. What we did here, we have a training set, and we learn kind of average set of wavelengths. Need to do better how we do that. Basically, the edges we detected, the average them. That is one set of wavelengths for the entire level.
Any other questions for Jérôme?
Are you doing convolutions with your neural network, or are you using like straight up regular neural network?
So the I mean, all those networks do have convolutional layers.
Okay.
Yeah. We didn't design a specific architecture. We use the existing ones. I mean, all those networks that we tried were basically top 4, top 5 neural net architecture in textual analysis. We just retrained them using the empirical wavelet coefficient. And it's time to stop.
One last question.
I have a question about the wavelength that you're using. So there's several different types of like other wavelengths, right?
Yeah.
That can be applied with it. So is there always an optimal place that you go for, or how do you define that search for the right one?
So the one I used initially, the one I showed you, the image that was the most natural one. Since then, I do have a paper where I investigated basically the use of any kind of model. Can do it because I define the formalism. What you can show is that the empirical wavelets. So this is a combination again of scaling and translation. The empirical wavelet, you can write them as a combination of scaling, translation, and modulation in a specific order. Right? And so based on that formalism, then now you can plug it into C. Okay. So yeah, and in the paper, I should say what example. You can do that more. Okay. And by the way, I have a WhatsApp toolbox. The link is on my website.
All right, so it's clear that Jérôme's throat is longing for some lubrication. So we're gonna go to the Eurekas to lubricate your throat. And thank you very much, Jérôme, for a very nice talk.